Previously, we looked at how you could describe a distribution by its center and its spread. We talked about the mean and the standard deviation. And then we went on to talk about how much data we would expect within one standard deviation, two standard deviations, and so on. And from 2 to 3 and beyond, we start to talk about outliers. Typically, that sort of description would be for data that's more symmetric. In situations where things are more skewed, another approach, not based on mean and standard deviation, is to use what's called a 5-number summary. And we talked previously about the median, right? So here what I've got is a distribution that's got a long tail on the right. So remember, that's going to pull the mean to the right. So this is skewed right. So we have this skewed right distribution. And so remember, the median is the one that's right, the value that would be right in the middle of our data. So let's just say that right there is our median. And we know that from skewing, the mean would actually be over here somewhere. This long tail is pulling the mean, skewing it to the right, so hence the right skewed distribution. So you can think of the median breaks this distribution up into 2 chunks. 50% of the data is on one side, and 50% is on the other. We could further subdivide. So the next thing we'll do is split those 2 halves in half into quarters. We call them quartiles. So let's say about here, that divides that area in half, and that divides that area in half. This thing you can think of as the median of the first half and the median of the second half. We call this one Q1 for the first quartile. We could then call the median the second quartile, and then this the third quartile. So what this does is it divides our distribution up into 4 chunks, all containing the same amount roughly. 25% of our data is in that first chunk, 25% in here, 25%, 25%. So it takes 3 cuts to get 4 pieces. So we have 3 quartiles, Q1, 2, and 3. And then there's some value out here in our data that's actually our max. And there's some value down here in our data that's called our min. So these values together, the min, Q1, Q2, Q3, and the max, are called the 5-number summary. And what we're going to do is we're going to think of the middle. We're going to reference ourselves off of the middle 50% there. So when we're talking about things in terms of medians and quartiles, one piece of information that is useful is, what is this distance how far is it from Q1 to Q3, that spread that covers the middle 50%? That distance is called the interquartile range, or IQR for short. So that distance, that interquartile range, is simply the distance from Q3 to Q1. So if our data is very tightly packed around the median, this interquartile range will be very small. If our data is very spread out from the median, this IQR will be larger. So you can think of IQR is in a sense going to be taking the place of standard deviation in the role it plays in this 5-number summary approach. And so because of that, it's going to be crucial in how we define outliers. So the question is how far past Q1 this way or how far past Q3 this way do we want to consider extreme and consider those outliers? And typically, we're going to say anything that goes 1.5 times, basically our yardstick is going to be 1.5 times this distance, that middle 50, so the interquartile range. So if you go below Q1, so if you're less than Q1 minus 1.5 times the interquartile range, anything less than that way, we will consider an outlier, or anything greater than that same distance above Q3. So sometimes we'll refer to these as our fences. These are our cutoffs. Anything past that will be considered an outlier. Anything within those bounds will not be considered an outlier. So the 5-number summary is that min, Q1, Q2, which remember Q2 is really the median that we talked about before, Q3, and the max. Next, what we'll look at is, so this gives us a way of describing outliers. Next, what we'll look at is you could take this 5-number summary and put it in a nice graph called a box plot. So we'll look at how all this can be put together to give a nice simple representation of the distribution of our data.